The optimal space filling design is one of the DOE models. We have already studied about central composite design or CCD and also box Benken design or BBD model. And now in this session we are going to study about optimal space filling design. The optimal space filling design model divides each input parameter into several parts. This design model is divided in terms of the number of sample points, and the values of these sample points include different types. Also, the number of input parameters in each model determines the number of divided points. This design model has several features. This model can distribute design points evenly within the design space. The goal of this model is to achieve maximum analytical vision using the least number of design points, and the placement of design points within the design space is heterogeneous. This means that in this model, unlike previous models, it is not necessary to place the design points in the corners or middle points. This figure shows the design space, including the design sample points, according to the optimal filling space design method. In this design space, two input parameters are considered, each of which is divided into 5 levels. The types of distribution of the sample points of the optimal filling space design model include the following: CCD samples, linear model, pure quadratic model, full quadratic model, and auto-defined. This figure shows the sample distribution types for the optimal filling space design model. When each of the mentioned models is selected, each of the input variables is divided into a certain number of sample points. We now consider the range of change in each of the input parameters and calculate the difference between the upper and lower limits of each of the input variables. And we divided this value by the number of points in the positive sample. The value of this division is equal to the distance of each of the points of the created sample from each other. If the number of points in the sample is an odd number, the point of the central sample or the mean value between the maximum and minimum is maintained, and this distance is added periodically to the top and bottom sides of these middle values as far as it reaches the maximum and minimum range of that parameter. If the number of points in the sample is an even number, ignore the point of the central sample, the mean value between the maximum and minimum and add half of this distance to both sides and above the below this intermediate value to create 2 points in the middle of this interval, and then add the full value of this interval periodically to the 2 middle and upward and downward points until it reaches the maximum and minimum range of that parameter. For example, suppose an input parameter has a maximum and minimum values of 90 and 110 respectively. Assuming that 3 input variables are defined for the software and the optimal space filling design method is used. The process of distributing sample points has been done in 2 ways: CCD design and full quadratic model. If the central composite design or CCD sampling type is used, the number of divided points for each of the input variables will be 15. As a result, we divide the distance between 90 and 110, which is equal to 20 to 15, which will be equal to 1.33. And since the number of points is odd, keep the midpoint of this interval, or 100, and add this distance of 1.33 alternately to both sides of the number 100. Now suppose that according to the mentioned pattern, we have an example that the radius parameter defined in the experimental design environment table has a range of change from 90 mm to 110 mm and uses the optimal space filling design model and the central composite design or CCD sampling type. This figure shows the table created in the ANSYS Workbench software. If a full quadratic model is used, the number of divided points for each of the input variables will be 10. As a result, we divide the distance between 90 and 110, which is equal to 20, by 10, which will be equal to 2. And since the number of points is even, we calculate half the calculated distance, that is 1. We add the 1 to both sides of the middle point of this interval, the number 100, to produce the middle 2 points of this interval equal to 101 and 99. And then we add this numerical distance equal to 2 alternatively to the two sides of the numbers 101 and 99. Now suppose that according to the mentioned pattern, we have an example that radius parameter defined in the experimental design environment table has a range of change from 90 mm to 110 mm, and from the optimal space filling design model and the full quadratic model is used. The following figure shows the table created in the ANSYS Workbench software environment. Master CFD experts are ready for DOE analysis, consulting, training, and CFD simulation. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.